In real life, there are many situations where one needs to evaluate integrals numerically. That is to say, we need a number for a definite integral. Now, suppose you're given an integral e to the minus x squared from 0 up till 3. There is no way that this can be done analytically because there is no function which when differentiated will give you e to the minus x squared. Nothing elementary anyway. And so people have had the need to invent ways of doing integrals approximately, numerically, and now with the computer and the calculator, it has become very easy to get numerical values for these integrals. This is what we'll do in this lecture. We'll first talk about the trapezoidal rule and then about Simpson's rule. Of course, these are just two rules and there are very many others that we won't be able to touch on, but that's a whole big field of numerical analysis that we won't get into. Let's begin with talking about which kinds of integrals need to be evaluated numerically. Let's begin by asking when we must integrate numerically. Certainly, if you can do integrals analytically, such as the one over here, 1 over 1 plus x squared from minus 1 to plus 1, this is an integral whose answer we immediately know because the answer is tan inverse x. If you differentiate tan inverse x, you get 1 over 1 plus x squared. And this has to be taken between minus 1 and plus 1. So that is pi by 4 minus pi by 4. So that's pi by 2. Here, we don't need to do anything numerically. That's because we had really an antiderivative over here. But what if one has something like this? Minus 1 to plus 1 e to the minus x squared. Now there is no function that we know of which when differentiated will give you e to the minus x squared. And so yes, you have to do this integral numerically, and we'll shortly discuss that. Now there are integrals that do not exist and they cannot be done by any method. We've discussed these as well. So if you go from minus 1 to plus 1, let's say of dx over x, this integral does not exist. So don't bother doing this numerically. The simplest way of doing numerical integration is by use of the trapezoidal rule. I'm going to derive this in two different ways. Well, trapezoidal comes from trapezium. Trapezium is the figure that you see over here. It's actually two figures. There's a rectangle with a triangle on top. Here is the function f of x, sketched in blue, whose integral we want from 0 to delta. So we'd like to have integral of f of x from 0 to delta. Unfortunately, f of x is too difficult to integrate analytically, and so what we shall do is approximate f of x with a straight line. So we shall write down the simplest polynomial which can do that. P of x is a0 plus a1x. When x is 0, f of x and p of x are both f0. When x is delta, then f of delta is f of 1. So let's now find out the coefficients a0 and a1. If you put x equal to 0, then p of x is f0, which is equal to a0 plus 0. So we found a0 equal to f0. Put x equal to delta now. P of x is f1, and that's a0, which is f0, plus a1 times delta, from which we get immediately that a1 is f1 minus f0 divided by delta. Now let's come back to this integral, which we've decided is to be approximated by the integral of this straight line, that is the polynomial, so that this is a0 plus a1x. And now this has to be integrated, which is easily done. So we have a0 into delta plus half a1 into delta squared. Putting in the values of a0 and a1, we get delta into a0, which is f0, plus half. This is f1 minus f0 over delta. And there was delta squared, but we took one delta out, and now this delta and this delta cancel. So what we are left with is delta into half f0 plus half f1. That is the area which is under this straight line, this red line over here. And you can see that although it is somewhat close to the integral of f of x, that is the area under f of x, it's not identical. So let's make a lot of partitions, and by doing so make delta smaller and smaller so that the straight line approximation becomes better and better. Let's see what the trapezoidal rule gives to us when we have more points. So we're going to chop up the interval between b and a into n points, and so delta will be b minus a divided by n. In this case, n is 4. So now the integral from a to b of f of x by the trapezoidal rule will be delta. If we call this f0, f1, f2, f3, and f4, then by the rule that we've just discussed, this will be half f0 plus half f1. That's the area under the first one. Then we take it for the second one, that'll be half f1 plus half f2. And now for the third one, half f2 plus half f3. And finally, the fourth one, that is to say, this one here. So we get half f3 plus half f4. Now, when we add this all together, we see that a rule comes out of this. That's the trapezoidal rule. The first point, f0, gets weighted by half. The second by just 1 itself. The third by 1. And the last one gets weighted by half again. So the rule is half, 1, 1, 1, 1, 1, etc., with the last one getting a weight of half again. I'm now going to give you a derivation of the trapezoidal rule that will give more insight into our first derivation and which will help us think through things more clearly. For this, I shall need to review Taylor's theorem, which we had studied in an earlier lecture. Taylor's theorem says that suppose f of x is a function that you can maybe differentiate forever, but which you can differentiate at least n plus 1 times, then f of x can be expanded in terms of a polynomial. So if x is exactly 0, well, you just need this first term. But if x is close to 0 but not 0, then you might be able to get by with just this term added on to the first. But if you want more accuracy, then you'll have to add on this term and so forth. The closer you are to 0, the more accurate you will be. And here is the remainder or the error that you make by stopping at any fixed value of n. Anyway, we're not concerned with what r is. All we need to know is that you expand as f of 0 plus the first derivative evaluated at 0 times x, and then the second derivative at 0 times x squared, and so forth. Before I come to the second derivation of the trapezoidal rule, I must tell you how to take derivatives on a grid. That is to say, how to approximate a derivative. So, Suppose that this is a function, f of x, its value here is f of b, its value here is f of a, then you know that this ratio f of b minus f of a divided by b minus a will get closer and closer to the derivative at the point A or the point B, but those points will be very, very close together anyway. And we write this as usual as f1 minus f0. The distance b minus a is delta. So of course, I've taken this to be f1, this to be f0. As delta gets closer and closer to 0, f1 and f0 get closer and closer, and this will be the derivative. Now, you can ask, where is this derivative being taken? After all, here, and this is one of the theorems that we discussed earlier, the derivative of this red curve here is exactly the same as that of this straight line. But elsewhere, it might be a bit different. It's only in the exact limit delta goes to 0 that the two will be the same. But anyway, now let's move on and ask, how do you take the second derivative? Here we needed just 2 points, f of a and f of b. Here we're going to need 3 points. So let's call this f0, f1, and f2. The distance between a and b is again delta, but from here to here, I've taken this to be the midpoint. It's delta by 2, and there's delta by 2 over here. Now, if we take the straight line over here, then the derivative in between the 2 points will be f2 minus f1 divided by delta over 2. That's the derivative of the curve, of the red curve, approximated by this straight line connecting these 2 points, and that's this derivative. Let's take the derivative between a and a plus delta by 2, and so let's take the derivative over here. If we take their difference, that will be f1 minus f0, and again divided by delta by 2. And now what we need to do in order to get the second derivative is the difference in the first derivatives divided by delta by 2. Why delta by 2? Because this distance from here to here is delta by 2. So this is now the definition of the second derivative, and we've approximated it now. So just now let's just divide out. We get f2 minus 2f1 plus f0 divided by delta squared. And this is approximately what you would call the second derivative of f in between a and b. Now, again, this is approximate. We're not saying that this is either at a or at b. It's best to say that it's somewhere in between them. Let me now come to the second derivation of the trapezoidal rule. For this, what we need to do is again the same integral dx f of x between 0 and delta, but now I'm going to use Taylor's theorem to expand out f of x. And so this is integral dx 0 to delta, and now f of x is f of 0 plus x times f prime at 0 plus half x squared f double prime at 0, etc. And I'm just going to stop here at the second order. We can now integrate this out. If I integrate a constant, I just get x, and that gives me delta. So I get delta times f of 0. But f of 0 I will call f0, and f here I will call f1. That's to be consistent with our earlier notation. And so I get delta f0. Then when I integrate x, I get half delta squared. So I get half delta squared f prime of 0. And now I have to integrate half x squared, which will give me a 6th x cubed. But I'm not going to be evaluating this term. That's beyond the trapezoidal approximation. And so we'll simply say that that is a term that is of order delta cubed. And by writing O of delta cubed, that means that these are the kinds of terms that we're going to neglect. So now let's do what we did before, that is take delta common, write this out, f naught, and then I have half delta. I've taken one delta out. I need the derivative of the function at this point. Well, for a straight line, that's the same as over here. And we talked earlier, just in the previous slide, how to take the derivative on a grid. And that gave us f1 minus f naught divided by delta. This delta cancels with this. And so again, we get delta into half f naught plus half f1. Of course, the error that we've made is of order delta cubed. So one value or one useful thing about doing the trapezoidal rule this way was that we were able to get an error estimate, that it's order delta cubed. Those are the terms that are missing from this analysis. Of course, as delta becomes smaller and smaller, this error over here gets smaller and smaller too. So we're pretty much done. As before, we could take this and then we'd again get the rule that the area under the blue curve is approximately the following. There's half f naught and then f1 and then f2 and then f3, and you keep going until you reach the last one where you put fn. In this case, n is 4. And so that's our second derivation. More accurate than the trapezoidal rule is Simpson's rule, and I'll give two derivations of that. Let f of x be this function which is plotted here in blue, and instead of passing straight lines through various points on the function, I'm going to take 3 points, this, and this, and pass a parabola p of x. Now the value of the function at minus delta, f of minus delta, I'll call f naught. The value of the function at 0, I'll call f1. And the value of f at plus delta, I'll call f2. The function p of x is quadratic. It's a polynomial with maximum degree 2. Next, we want to find out what a0, a1, and a2 are. That's easy enough. Let's first put x equal to 0. That means this is f1. And putting x equal to 0 here and here will just give us a naught. Next, let's put x equal to minus delta, in which case p of minus delta is f naught. And we get a naught is f1, of course, plus a1 into minus delta, plus a2 into delta squared. Finally, let me put x equal to plus delta, and that's f2, which is a naught, again that's f1, plus a1 into plus delta, plus a2 into delta squared. Okay, so now let's add this equation to this equation, in which case we get f0 plus f2 equals 2f1. These two terms cancel out and we get 2a2 delta squared here, which means a2 has been found to be f0 minus 2f1 plus f2 divided by delta squared 2 over here. Now, let's ask what is the integral from minus delta to plus delta of p of x. And of course, the hope is that this area which is under the red curve will not be too different from that under the blue curve. Let's work this out. So that's the integral from minus delta to plus delta of what I've written above, a0 plus a1x plus a2x squared. Now right away you notice that this is an integral that you don't need to do because this x is an odd function and we are integrating symmetrically from minus delta to plus delta, and so this integral we don't need to worry about. The only thing that remains is a0 into 2 delta, but a0 is f1, so that's f1 into 2 delta. Then the next thing we need to do is integrate x squared, so we'll get 1/3 a2x cubed from minus delta to plus delta. And so this is f1 into 2 delta plus 2/3 a2 we have above, that's f0 minus 2f1 plus f2 over 2 delta squared, and of course there's delta cubed over here. Now this delta squared will go with 2 powers over here, this 2 will go with this, and when we write this out, this is, let's take delta over 3 common. This then becomes f1 plus, f0 plus 4f1 plus f2. And that's the area under the red curve over here. Now it might seem as if I'd made a very special choice of axes and that this is not perfectly general. After all, what I did was I took one extreme point to be minus delta, the other extreme point to be plus delta, put the origin in the middle over here, and then calculated this integral from minus delta to plus delta of the quadratic p of x. And what I found was delta 1/3 of f0 plus 4/3 of f1 plus 1/3 of f2. But what if the curves had been shifted like this? So f of x now is at a different part of the x-axis. This point, which was at minus delta earlier, now is at a. And the question is this integral from a to a plus 2 delta of p of x the same as what we have on the left-hand side? And the answer is yes. It's very easy to prove because let's make a change of variables. Y is x minus a minus delta, in which case if you take x equal to a, then y is equal to minus delta. If you take x is equal to a plus 2 delta, which is what is above over here on the upper part of the integral, then y is plus delta. And so since dy is the same as dx, then we have exactly the same integral. We have dy with y going from minus delta to plus delta, and Instead of p of x, we have p of y, but that makes no difference because this is a dummy variable of integration. And so this has exactly the same value as over here. And again, this will be f0, and this will be f1, and this will be f2. Let's now use this to get Simpson's rule when we have any number of partitions. So let's take the partitions from A to B. Of course, delta will be B minus A divided by the number of partitions, which in this case will be n equal to 4. And so we will have 4 partitions. This will be delta here, delta here, delta here, delta here. And so the integral from A to B of this function f of x will be delta. And now it'll be 1/3. Let me now label this f0, f1, f2, f3, and f4. This will be 1/3 f0 plus 4/3 f1 plus 1/3 f2. What I've done effectively is pass a parabola through f0, f1, and f2. So now I have this area, which has been written below over here. Next, let me take a parabola and pass it through f2, f3, and f4. And of course, I should have then 1/3 f2 plus 4/3 f3 plus 1/3 f4. And now let's just add up the various terms. So I have 1/3 f0 plus 4/3 f1 plus 2/3 f2 plus 4/3 f3 plus 1/3 f4. Now I think the pattern should be very clear. If I have, let's say, n divisions, n partitions, the first will have weight 1/3, the second will have weight 4/3, then 2/3, 4/3, 2/3, and we'll keep going until we get 4/3 and then finally 1/3 again. These things, 1/3, 4/3, etc., are called weights. We saw just a little while ago that it really doesn't matter where you choose your axes. So again, I'm going to choose them conveniently. The function at minus delta is f0, at 0 it is f1, at delta it is f2. I am not going to make any use of this polynomial p of x at all. It's just there because it was there earlier. What we want is this integral, the integral of f of x from minus delta to plus delta. And I'm going to use over here Taylor's theorem and expand out f of x, which is f of 0 plus x times f prime of 0 plus half x squared second derivative at 0 and 1 over 3 factorial, which is 1/6 x cubed, the third derivative at 0, etc. Now, when we do this integral, or the different integrals inside it, we get, first of all, f of 0, which is f1 into 2 delta. The second integral is the integral of x between plus and minus delta, so that's 0. It's an odd function. The third integral will give us 1/6 x cubed between minus delta and plus delta, f double prime at 0. But what is f double prime at 0? Remember that this is f2 minus 2f1 plus f0 divided by delta squared. That's what we had found when we looked at the second derivative on the grid. Okay, so now let's write this out. This is 2 delta f1 plus, now from here we get 2 delta cubed, and so we get 1/3 delta, and all of this then, f2 minus 2f1 plus f0. And of course, when you take delta out, this is exactly what we had earlier. This is 1/3 f0 plus 4/3 f1 plus 1/3 f2. Here is what we've achieved so far. According to the trapezoidal rule, we break up the interval between b and a into n equal parts. Then the integral between a and b is then just delta, which is the length of the interval divided by n, times the value of the function, which we've decided to call as f0, f1, f2, f3, f4, etc. And so the trapezoidal rule gives us weights half, then 1, 1, 1, and then half. Whereas the Simpson's rule that we derived gives us weights which are 1/3, 4/3, 2/3, 4/3, 1/3. And of course, this can be extended on. This is the general formula for Simpson's rule. To compare Simpson's rule with the trapezoidal rule, let's take a very simple example. F of x is sine x, and what we want is the integral from 0 to pi of sine x, and of course that's trivial. The answer is 2. Let's take n equal to 2. So just 2 partitions. Delta, the grid spacing, is then pi by 2. And so obviously f0, which is here, is 0. f1, which is here, is 1. And f2 is 0. That's here. So the trapezoidal rule tells us that the value of the integral is delta, which is pi by 2, half f0, that's 0, plus 1, that's the weight, times f1, that's 1, plus half times 0. And so that's just pi by 2. Pi by 2 is just 1.57. Compare 1.57 with 2 and, well, we're like 75% of the answer, but that's 25% missing over there. Let's now do Simpson. So here the only difference is that the weights are different. The weight for the first point is 1/3. The weight for the second point is 4/3. And the weight for the third point is 1/3 again. So that's now 2/3 pi. And if one just looks at a calculator, that is 2.094. 2.094 is quite a bit closer to 2 than 1.57. And so clearly, the use of Simpson's rule is much better. Clearly, a parabola is doing a much better job than two straight lines. Let's repeat with the same function, which is f of x equals sine x, and we want the same integral, that is to say from 0 to pi of sine x, whose value is 2. But now I'm going to take more points, n equal to 4. That means my grid spacing is now pi by 4. And we're going to need the following values: f0, which is sine of 0, which is 0. f1, which is sine of pi by 4 here, and that's 1 over square root of 2. f2, which is sine of pi by 2, that's 1. f3 will be here, so here we have 3 pi by 4, and the value, the point f3 will be this, just like f2 was this, and f1 was this, and f0 was this. So f3 is again 1 over square root of 2, f4 is 0. And of course, here, in this other graph, the values will exactly be the same. Let's now use the trapezoidal rule. So the value of the integral, according to the trapezoidal rule, will be pi by 4. We give half weightage to f0, then 1 weight to f1, which is 1 over square root 2, 1 weight to f2, 1 weight to f3, and half weight to f4. When we use a calculator for this, the answer is 1.896. That is better than what we did with n equal to 2, but this is not very close to 2. Let's now use Simpson. And the only difference again is in the weights. Instead of what we have above, we have 1/3 times 0 plus 4/3 times 1 over square root 2, then 2/3 times 1, 4/3 times 1 over square root 2, and then finally 1/3 times 0. Working this out, we get something that's much closer, 2.005. So that can be compared against this, and clearly Simpson's rule is much more accurate than the trapezoidal rule. But of course, there are things that are better than the Simpson's rule as well, which we haven't discussed. You will have noticed that I took a very smooth function, sine of x. If I had taken something else, 1 over 1 plus x squared, that too would have been very smooth. But what happens when you have a function like, let's say, sine of 1 over x, and you integrate from, let's say, -1 to +1? Here is a function that goes up and down, oscillates very rapidly, and there numerical integration will get you into trouble. So, when one does numerical integration, the first thing to do is to look at the integrand and then to figure out what can be integrated numerically and what cannot be. But we will not get into too much discussion on this. This was just an introduction to numerical integration.